Now let us look into the sign division. So whatever we have discussed so far is unsigned value, okay, unsigned division, and that's the circuit. So in the sign division, we'll take the same strategy as we did in the multiplication. So in the similar way as we did in the multiplication, we pick up the value of the dividend and divisor irrespective of its sign. Okay, so we need to deploy a 2's complement circuit. We are not showing that inside what is there. It's already being discussed on in the multiplication when we discuss the sign multiplication. So we deploy the 2's complement and convert the dividend and divisor from its signed value representation to its absolute value, like a positive if it is a negative, right? And then feed it into the unsigned dividend, and then divider gives you quotient and remainder, right? Unsigned. We blindly convert it into its negative, like opposite sign, sorry, negative actually. This is unsigned value. So we have unsigned or the positive value, or complement, we make a 2's complement again and then make a negative representation of that quotient and negative representation remainder. And then what we all need to do is to pick up the right sign. So according to the sign of the quotient and remainder convention and operation direction. So you all know for the quotient it follows simply the multiplication sign strategy. It's positive, both positive is positive, both negative quotient is negative, then positive negative combination gives the quotient as a negative. So it's the same as your XOR logic deployed between the MSB of dividend and divisor to determine what is the sign going to be for my quotient, and we pick up the corresponding value, corresponding representation through the multiplexer. This is 2 to 1 32-bit multiplexer. We pick up the corresponding value accordingly. And as I discussed very beginning of the divisor circuit discussion, that digital convention is that your remainder has to be same as your dividend sign. By the algorithm we deployed here, it ensures that your remainder will be same sign as of your dividend. So our dividend remainder sign representation pickup, like selection, is only depending on the sign or MSB of the dividend. So we just use that MSB of the dividend as a selection logic of this 2 by 1 32-bit multiplexer for the remainder to picked up as either is complement form, which is a negative representation, or its positive representation. So this is how we do the sign division, at least at this digital level. Now point is this, like remember we talked about the rollback, and it has one more significance. Unlike multiplication, we cannot have a combinational division circuit. Why? Because if you recall, multiplication we could do it as a combinational circuit because stepwise it is always forward propagating. Like we do partial product computation to multiply partial product. We never have to go back and revisit a result, right? But division by algorithm itself, we are trying a subtraction, and at that point, if it is a negative remainder, we just rolling it back, right? So we are not always a forward propagating. At some point of time, it's possible that we need to go back one step. We need to do that, right? So that's why it is not possible for a divider to have a combinational circuitry. And this is one of the reasons I also did not include division as an instruction in CS147 DV, because at the gate level, when we'll be doing the gate level circuit design project 3, we'll do multiplication implementation as a combinatorial circuit. That's why multiplication, I put it as an instruction set, instruction in the instruction set of our target CS147 DVISA, but not the division, because there is no way there is a combinational circuit we can make with it for the division, and I don't want us to get into the complexity of making a sequential division circuit. So that's why I carefully avoided, strategically avoided to place a division operation as an function supported by our target processor. Now, does it mean that our target processor is not like of any use because it doesn't have a division circuit? Of course not, right? Look at the algorithm. It has what? It has subtraction, it has addition, it has shift. All of these are already part of your instruction set. All this, like you have add instruction, you have sub instruction, you have shift instruction. So you can write a software library which runs the same algorithm as described for division and make a division as a software library. So earlier days, in fact, like division, when this complex circuitry technology was not evolved, it has only like this primitive add and subtraction operation. Multiplication division could have, or in fact they were a part of the software. Okay, they're part of the software and we can do that. In fact, like if you think of floating point operation, even for the addition, addition subtraction, is a lot more complex step, and not that early computing system did have a dedicated hardware for those floating point addition, subtraction, multiplication, division. They are all done through software libraries and through this basic logical bit operations. Like you can do addition, you can subtraction, you can do integer multiplication, integer division, and you can deploy all these operations and make a library software library for floating point operations. Only lately, for the modern computers, where technology has been evolved to kind of map the software algorithms onto the hardware circuit, coprocessor has been developed for the dedicated for the floating point operation. Okay, so this is the same philosophy here. We don't support division operation in our toy processor. That doesn't mean we cannot do anything with that. We can still write a division operation in the software and make it a part of the whole system, so that whoever writing application software on top of this processor does not feel that it has some restriction on writing anything. Okay, so that's the point you need to understand. Just to give back your MIPS division instruction, what MIPS process as a processor it gives, it has a div, and your low is basically remainder, high is basically the quotient. It might be other way, not important at this phase, but if you're interested, please look at the MIPS instruction set architecture and what it says about div operation. And we have this move from high and move from low to access those data from those areas, right? So if we ever plan to make a sequential division in our like project or anything, not really, like this semester is out of scope that perspective, but we could have done that in the similar notion as the MIPS does, have 2 extra register and some sequential circuit be implemented, at least at the behavioral level. Okay, so we could have done that. So that's all for this lecture 10. If you have any questions, send me email or ask me in the class.